For this teaching worksheet, differentiation 1A, we are going to start the section on this thing called calculus. So in your A Math syllabus, you will have a calculus section. So this calculus section has two parts. Okay. It's two big parts of A Math syllabus. So one part will be differentiation, another part will be integration. So essentially, integration is the opposite of differentiation. So right now, you wouldn't know what is what yet. So this is under the big field of calculus. So under differentiation, right, we're going to split into two sections. We're going to split into the technique. And later on, we will split into application. So the focus for this first teaching worksheet 1A is on technique. So before we talk about technique and what are we going to do for technique, under the technique part, there's a couple of formulas. So in total, there are 5 formulas under the technique part. So there are 5 formulas under the technique. And application, there are, I think, depends on how it's being classified. It's around 3 to 4 applications. So the technique will affect your application, of course. So okay, before I go into technique, I need to introduce you the idea of notation. Okay, so the typical notation, we will be starting off with function of x. So y as a function of x. So when y is a function of x, after you apply the technique of differentiation, so after you apply any of the formulas under the technique, you will be getting something called dy dx. So after you apply the 5 formula, you'll be getting a dy dx. Okay, let's see whether you can see the pattern in the notation or not. So if let's say you have an area in terms of x, so an area formula in terms of x, after you apply any of the 5 formula under the technique, you're going to be getting dA dx. So can you see the pattern in the notation? So if it's y and x, it will be y on top and x below. If it's a and x, it will be a on top, x below. So it's very important you don't mix up the notation. So once the notation is mixed up, in fact, one of the application might be compromised, or you will feel that it's very confusing for one of the notation. So I will give you 2 more examples. So for example, maybe I will have y in terms of r. So maybe how do you, like maybe I got y equal to pi r squared. So y is a function of r. So in this case, if I apply any of the formulas, any of the 5 formulas under the technique, I will get a dy dr. Okay, or maybe I will have a volume formula, and my volume is in terms of x. So something like v equal to x cubed. Then if I apply any of the 5 formulas under the technique section, I'll be getting a dv dx. So that is the notation that you need to take note. So the usual term will be you will differentiate with respect to x, you will differentiate with respect to r. So when we say differentiate with respect to x, you will be getting a dx. When we say differentiate with respect to r, you will get a dr. So differentiate with respect to x, then I will get a dx. So these are the few category of notation. So just an example. So will you come to the part where there is area and volume? Yes. There will be one section where it involves volume and area. So whatever you learn in E-math, the maturation formula, like volume of cylinder, volume of cone, all these will be applicable. And in the A-math section, usually you're not provided with the formulas. So you have to remember the formulas in this part. So this will be the main section about the notation. But today our focus is on this part. I will be focusing on this part. So to start with, we are going to focus on the function of y and x, and we are creating this dy dx. So the creation of dy dx, right, is actually this thing that you're going to create using the 5 formulas will be known as a gradient function. So we are going to create a gradient function. So sometimes we also call it gradient formula. So there's a lot of names for dy dx. So one of the important thing is to recognize that what are you achieving after your 5 formulas. So when you get the expression for dy dx, right, what is this expression for? So this expression is known as a gradient formula, or sometimes some people will call it a gradient function, or sometimes we will call it gradient of tangent. So there's a lot of concept relating to dy dx. So this dy dx function that you create based on the 5 formula that you will be learning, okay, will form a few of the application. Okay, so basically you're creating a gradient formula through the 5 formulas. So today we will not be able to discuss all the 5 formulas. So I'm just going to introduce you with the basic formulas first. Okay, so just a quick summary before I go to the formulas. So this is the start of calculus. Calculus is divided into 2 sections, differentiation and integration. So if you are going on to JC, there will be a chunk on calculus as well. And for those of you, if you intend to go poly in some of the engineering courses, there will be some amount of calculus as well. Okay, so I'll be erasing everything and I'm going to introduce you the formulas. So make sure you copy everything first. Okay, I will need the space to introduce you the formula. So, but I'll be leaving the notation of dy dx at the corner. So that's one of the key things. So we are trying to apply the formula to create a gradient formula, to create a gradient function, or what we call a gradient of tangent. So let's look at the first formula here. So the first formula is applicable when y is a number. So k is just a number. So for formula number 1, it is applicable when you see a number. So when you see a number, right, when you differentiate, you will get a 0. Okay, you can just take it as a formula, or if you want to understand why. So in a graphical way, this is a horizontal line. So all of us know that horizontal got 0 gradient. And if you recall, what is dy dx? dy dx is a gradient function, is a gradient formula. So that's why the gradient is 0. So y equal to a number is a horizontal line. So a horizontal line doesn't have gradient. That's why if you differentiate a number, you don't have any value at all. So you might want to see it that way, or you might just want to see it as a formula. It's up to you. Okay, so that is the first basic formula. Now, the second formula will involve x as a function. So if you look at the second formula, it is meant for axn. So if you look at the second formula, it involves something called, the function will be something like axn. So for this formula to work, you need to make sure that the x and the constant are side by side. So this must be side by side. So in a situation where maybe you got something like this, it doesn't work because the x is at the bottom. So in such a situation, you actually need your indices to make the x and the number side by side. So later on, there will be some amount of indices. So there is a condition for to apply rule number 2, x must be side by side with the constant. Okay, then after that, how are you going to apply the formula? So the formula will be in terms of something that you can keep saying in your heart. So these are the 2 steps that you need to keep saying. So you are going to bring down the power. So can you see? I literally bring down the power and I minus the power. So to differentiate something with x, if you ensure that x is side by side with the constant, you can just do a bring down power minus power. So formula 2 is characterized by the term that we will always say bring down power minus power. So you keep saying that. So that one will be basically the second rule. So you must understand the condition when you can apply this rule. So just now I introduced you the notation, I introduced you dy dx. So I also introduced you the 2 basic formula to apply so that we can get the gradient function dy dx. So now we go a little bit in depth into how you can visualize this. So again, I mentioned here, the dy dx is actually a gradient function of the curve. So it is like a gradient formula of the curve. So it is a formula that helps you to calculate gradient. So if you still remember in your e-math, usually you are asked to draw out your curve. Okay, if you still remember, so in the e-math, right? So you will do this on graph paper. So it's always this kind of question always appear on in e-math paper too. So usually there'll be a question, find the gradient at x equal to maybe x equal to 3. So you will draw a tangent and then you get 2 points to calculate the gradient. So usually in e-math, this is what you do. You got to draw a tangent with your ruler, then you apply your gradient formula. So you got to apply your gradient formula and then to find the gradient of tangent. So right now, if you already learn to differentiate, a dy dx, right, is also has an alternative notation. So in the recent year, right, you will see this notation, f prime. So if you apply any of the formula, so that become a gradient formula. And then when you want to find the gradient at x equal to 3, so you substitute x equal to 3 inside. So that one we'll talk more about it. So there is another notation that you need to take note. So this notation is called f prime. So recent O-level, they actually use this notation of f prime to represent dy dx, which is also a gradient formula. So whatever is it, dy dx will be gradient formula, f prime is also a gradient formula. There's just different notation with it. So if let's say I'm going to change the gradient to another point, so for example, right now I'm going to change my gradient to x equal to 1. So in e-math, I need to redraw and recalculate. But if I already got the formula, if I would like to calculate the gradient at x equal to 1, so I just substitute x equal to 1 into my gradient formula. So once I get the formula, I can plug in any x and I can find any gradient that I would like. But in the e-math part, whenever you want to change the gradient, change the coordinate, you will have to redraw and recalculate. So we are calculating, we are coming out with a gradient formula with the 5 basic formula. which today we're going to learn the two formula. So I'm going to extend the idea to the first example first. Okay. So basically you learn two formulas right now. First formula is meant for a number. Second formula is meant for when x is side by side with a number. Okay, so how are you gonna differentiate a cubic function like this? So if you look at the cubic function, we're going to differentiate one by one. So you might want to decide, this one looks like my formula number 2. This one looks like my formula number 2 as well, because the x is side by side with the number. And whereas this is just a constant, so that looks like my formula 1. So I'm going to apply formula 2 on the first term. So when I apply formula 2, I will bring down the power and I will subtract the power. So for minus 3x, the power is 1. So minus 3x, the power is invisible. So when you try to apply formula number 2, when you bring down the power, you are bringing down 1 as a power, and you will subtract the power. So if you are wondering, every time I subtract power, is it always a subtraction of 1? Yes. When I say minus power, it's always subtract 1. We do not subtract more than 1. And then the last one, if I differentiate 9, I will get a 0. So in a way, from here, if you try, you will see that this will become a 12x squared. And this will become a 3x 0. And if you remember from your indices, x to the power of 0 will be a 1. So that will be my gradient formula. So if you're thinking, right, do you need to write all this? No need. So in a while, you'll be fast enough to execute your bring down power minus power mentally. So you can just straight away give the answer. So you do not need to show the bringing down unless you find that it's very confusing. So there are some examples that are a bit confusing because they involve indices and algebra. So basically at this stage, you need to understand you already learned two formulas to achieve your dy dx. And what's your dy dx? Your dy dx is the gradient function, is the gradient formula, or gradient of curve, or gradient of tangent. There's a lot of name with it. In a nutshell, it's just a gradient formula.